set up the system. Let's just treat it kind of like water. Water flows downhill. Water flows to a lower potential energy, and by consequence, a lower potential. So, why do like charges why do like charges repel? Well, if I have a positive charge there, the electric potential coming from it gets smaller as we go out. So the electric potential, V, goes down as we get farther out. Positive charges like going to lower electric potentials. And since it likes the lower electric potential, as we get farther out, V gets smaller, positive charge goes towards it. Negative charges, on the other hand, which I think the electrons were figured out after Franklin was gone. Negative charges move to a higher potential. And I had asked a question where I had some mystery charge that went to, say, there. Is it a positive or negative charge? It would have to be a negative charge.
So this is yet another way to explain.
So now we have 4 ways of explaining why light attracts, opposites repel. Or, as most people would say, and the correct way, opposite attract and light repels. I think I just said it backwards the first time.
Negative charges go towards higher potential.
Yes. So we no longer have to think about what creates this electric potential, or these equipotential lines. We just know that if I stick a negative charge there, it's going to move to the higher potential. It wants to move to the higher potential. I can force an electron to move to a lower potential, but it would eventually stop if it's not going too fast, and then turn around.
Is it vice versa? Positive to lower, yeah.
So does this explain like the sublevels in the electron cloud of like an atom?
Oh, the SBDF?
Yeah, or is it separate? Because if it's that, I feel like that makes sense. Like electrons moving towards a higher potential, like towards the nucleus.
It's all connected. The difference in the SP, the whole electron shells and subshells, etc., are quantum physics, and all quantum physics, if you scale it up, should go to classical physics. So quantum physics deals on very tiny levels, but if you take it to an extreme, the limit should be what we teach in classical physics. So does it apply? I would say yes, it does apply. The derivation of the levels we might get to before the end of the semester, because that's the path we take at the very end, near the end.
Do the electrons
It does deal with kinetic and potential energies in the derivation. That's the sort of the starting point when we derive what the quantum numbers are. So I would say yes, it does relate.
electrons actually do go towards the inner shells. It has some that are on the inner shell, and then the free ones that are outside, right?
Yeah.
So which
So
ones
they-
are?
Those are just
moving- How are any of them moving towards the nucleus?
They like jump.
That's their tendency. So if I had an orb, I got my proton, or I have my nucleus here, electrons zipping around it. It gets hit with a bolt of energy, it gets jumped up to a higher level, it's unstable there. If you zap it with enough, the electron's gonna go flying off. If you do it just enough so that it stays within orbit, it's gonna go to a higher level, but at some point it's gonna come back down.
So they jump into closer to the nucleus and then they go back
They jump farther away and then they come back.
to an outer
It's-
shell. then.
Yeah,
Oh, okay. Wait, isn't that less potential then?
No,
If-
there's more.
no, if you-
The potential energy.
as you get close, the electron gets closer, it's going to a higher potential.
Yeah, but you just said they went out.
If you zapped it with energy, you have to hit it with something.
Oh, okay.
You take a laser or something, some light source that comes in, photons come in, hit the electron, jump it up, to give it enough energy to escape, and then it comes crashing back down.
Did it come crashing back down to a higher potential again?
Or if you zap it with enough energy, it leaves and never comes back. I was going to make a Lord of the Rings reference, but it was too much of a stretch. So what's left here?
Calculus.
Yeah, the calculus piece of it. We don't have enough time really to do the calculus problem, but sort of the teaser. If I have a uniform distribution of charge here, what is the electric potential at a spot? We've done electric field, now we can do electric potential.
Is it easier than the electric field?
We're not doing, trig doesn't come in. Well, does trig come into it?
Yeah.
We don't have to worry about the components. So yes, I would say it is easier. And also, the math relationship between these, which we'll get into. How many of you are in or have had Calc 3? So that part of the room. Do you know what the NAPLA is?
We haven't gotten to it yet, if we're.
Okay.
I think we're just kind of finished on partial derivatives.
You haven't seen that formula that yet? That's something over.
Oh, for differentials, I think differentials.
Oh, it's in differentials? Okay. All right.
No.
I know it's in Calc 3. I flashing.
Yeah,
I
definitely
don't remember
haven't-
it's being in differential.
Definitely haven't had that
It's been a
yet.
few decades. It's known as the NABLA, although good luck with word games.
Towards like the end of Calc 3.
Pardon?
You see it towards the end of Calc 3.
Oh, okay.
Yeah, I remember it. It's been a while since I've seen it.
It's known as a vector operator. It does not have any value in and of itself. It has to do something. So if you do the NABLA, do this operation against the scalar, then you're going to produce what's known as a gradient. This is also, some generic letter. This is also known as the gradient of x. We can do a dot product against a vector. This would be known as div of x, the divergence. And you can do a cross product with a vector, and this is known as the curl. If you want an intuitive feel for this, for those who are in Calc 3 or will be taking Calc 3, I do recommend, and maybe there's a better source now, but there's a book called Div, Grad, Curl, and All That, which to me gives, it helped me with the best conceptual view of this stuff. Div, Grad, Curl, and All That. I would recommend it.
Oh, so we're probably gonna be doing it tonight.
Okay.
Yeah, because it's in 14.6.
And as Porky Pig says, that's all, folks.